So I guess your mic is still muted.
Sorry?
So I guess your mic was muted.
So I haven't started yet. So if you can watch the screen and hear me, then I can get started.
Yes, so we can.
So I think today's lecture is really the heart of the um, of this chapter, because we get to the mass balances um, that apply to to um, to this class of problems. So as I noted last time, in the first chapter we wrote balances for substrate, biomass, products, so on and so forth, but we never wrote a balance for the gases. Here we'll see the gas balance for the first time, and I'm going to focus primarily on oxygen. So a slight notational change. I think it's better to show partial pressures. So wherever I wrote a C, I'm replacing it by pi, which is the notation for partial pressure. And I'll explain this in a minute. Okay, so here is our notation. Actually, for the sake of simplicity, I will also write S. And right. Okay. So the the notation that I'm using for the liquid side is the one that I've used before, which is F is the flow rate of the liquid. And as I mentioned last time, in biological reactions, because the density does not change, the flow rate in is equal to the flow rate out. And the feed concentrations will be depicted with F in the subscript. And so, for example, standard notation was PF for the product in the feed, and X sub F for biomass concentration in the feed. But of course, we've been assuming that there is no product and no cells coming into the reactor. So these two quantities are typically zero. And within the reactor, we assume that we have concentrations S and P and X, which have no subscripts at all. So when I have no subscripts, I'm referring to the concentration inside the bioreactors. And I will choose a similar notation for the concentrations on the gas side. So, well, before I do that, I would just want to point out that if we assume that the liquid is well mixed, then we are basically saying that the concentrations coming out, so the concentrations over here in the effluent, are given the subscript out. So you can see that S out is equal to S, basically says that the concentration coming out is equal to the concentration inside the reactor, which is basically a consequence of this. All these, in fact, are a consequence of all these, are a consequence of the assumption that the liquid is well mixed. This is the assumption that we are making, which is a reasonably good assumption for small scale reactors. These reactors are run at an RPM of rarely less than 400 RPM. So if that, convert that to per second if you want to get a feel for it, like divided by 60, 6 revolutions per second. Yeah, so that's pretty rapid agitation. it's reasonable to assume that the reactor is well mixed. So now let's get the notation clear on the gas side. The flow rate of gas going in, this is in liters per minute, is, so I put the subscript in and G. G, whenever I have a G, I'm referring to the gas side, just to distinguish it from, you know, the stuff that's happening on the liquid side. And the partial pressure, this is in, of course, atmospheres or whatever the unit of pressure you choose. And you know, there are other things you need to remember, like there is an inlet pressure and an inlet temperature. So whenever I have this is T out and P out, and these will be required later on when we use the ideal gas law. Now, the gas flow rates, as I mentioned last time, need not be equal to the gas flow rates. So, in and out are not equal, simply because, as I told you, the cells inside are converting oxygen to carbon dioxide, and that stoichiometric ratio is 1 is to 1 only under aerobic conditions. The more you deviate from aerobic metabolism, in other words, the more you do substrate level phosphorylation as opposed to PCA cycle oxidation, the more CO2 you get relative to O2. So, you know, you may get 4 moles of O2, 4 moles of CO2 per mole of O2 if you are metabolizing under highly anoxic or anaerobic conditions. And that means that the flow rate out will be bigger than the flow rate going in. So cannot assume flow rate in equal flow rate out. Okay, so my notation is pi O in for partial fraction, for partial pressure of oxygen going in, and pi O out for partial pressure going out. And once again, I will assume that the gas is well mixed. But if I assume that the gas is well mixed, it basically means that I am assuming that pi O out is equal to pi O. That means the partial fraction of the gas in the headspace is essentially equal to the partial pressure of oxygen inside the bubble. So pi O denotes the partial pressure of oxygen inside the bubble. Is that part clear? Is there any questions about the notation before I proceed?
Yes, that's clear.
Okay, so now okay, so now let's write. So we will start. So basically, we have assumed, as I mentioned last time, that I shouldn't say bubbles or gas phase is well mixed, which implies that the bubble and the headspace have the same concentration. This I should correct. Yeah, Mm. They have the same concentration. Okay, so that means that I will repeat that here. The assumption here is that pi O out is equal to pi O. Okay. This is actually this is not required. This will come later on, maybe as a very special case. Okay. So with that, we are ready to start. Okay. So now, if I take, going to take this is, so I have to be specific. What I'm doing first is I'm taking a mass balance specifically on the liquid phase of the chemostat. So I should actually say on oxygen in liquid phase. So what I mean by that is, if you focus your attention on uh, the reactor, and I will label the reactor with a red pen, this red portion captures what is really here. This is the real part. This is the working volume of the reactor, right? I mean, what sits on top of it. So this portion is often called uh, working volume. This is what is called working volume. And the top portion is called headspace. So I'm concerned about what is happening in the working volume of the reactor. The working volume of the reactor has both liquid and gas. And I will assume that VL is the volume of the liquid and VG is the volume of the gas. I think I defined it last time when I talked about the gas holdup. So VL will be used to denote the volume of the liquid, and VG will be used to denote the volume of the gas. Now, the balance that I'm taking is exclusively on the liquid. I am deliberately excluding the gas phase. Okay? So that, having made that distinction, so let me underline that to emphasize this is the liquid phase. So the first thing I have to write down is that this is the mass balance. So the first thing is, how much oxygen do I have in the liquid phase of the reactor? Well, CO is the notation that I'm using for the concentration of oxygen in the liquid phase. And VL is the total volume of the liquid in the working volume. So, how shall I put this? Maybe I should draw an arrow here. It's getting a little too busy, but just like pi o is the concentration of oxygen in the gas phase, there is a certain concentration of liquid, of oxygen in the liquid phase. This is also called dissolved oxygen concentration. So maybe it's in the liquid phase. This I denote by CO. This is moles of oxygen in the aqueous part of the reactor. Okay. So this is moles O2 in liquid phase, right? Or I should say moles of O2 per liter of liquid phase. Perhaps that's a better way to put it. And this is, of course, the total volume of the liquid phase. This is volume of liquid phase in liters. So the question we're asking is, how does this quantity, which describes the total amount of oxygen that is in the liquid part of the reactor, how is that changing with time? And well, we can see right away one quantity, one way in which oxygen is coming into this red rectangle over here is, of course, the liquid stream that is coming in, right? So this liquid stream coming in at flow rate F and SF is probably also carrying some oxygen with it because the feed tank has been sitting in contact with the air, and I will denote that oxygen concentration, let's say by COF. So this is the concentration of oxygen in the liquid phase of the liquid feed that is coming in. So this will be equal to F multiplied by COF, and let's say it's going out at concentration CO. So coming back to the picture over here, um, the concentration of oxygen going out is CO, coming in is COF. I hope that this, this is actually, so maybe I could even write down CO out is equal to CO, right? So this is another attribute or another property that results from good mixing. Of course, this is not the only way in which oxygen is coming in. We have just gone through a long derivation trying to capture how oxygen moves from the gas phase to the liquid phase. And the expression that we derived was essentially, we said that the flux is KL multiplied by CO star, right, which is the concentration of oxygen at the interface. This is in the liquid phase, and in the liquid part of the interface, minus CO. And of course, this whole quantity is based on per unit area. So it has to be multiplied by the total interfacial area in the liquid volume, right? So this is basically, this is interfacial area, total interfacial area in the working volume. So AI represents the total interfacial area in the rectangle marked by the red portion. So this is the amount that's coming in, and keep in mind that this CO star, as we went through it, is nothing but by equilibrium. This CO star is nothing but HO divided by pi A, where pi A is the concentration of oxygen inside the bubble, right? See the part that is denoted there? Let me mark it in green so that it is clear. This is the concentration inside the bubble. This is the bulk concentration inside the bubble. And CO star is the equilibrium concentration corresponding to pi O. So essentially, the picture over here, if I can draw it again, is essentially, if on the left side you have the bubble, the concentration is equal to pi A all the way to the end with no drop whatsoever, even across the film. And then on the right side, it here you have pi A, then here you have the concentration CO star, which is the concentration that is in equilibrium with pi A, and then it drops from CO star to CO. So all the resistance is confined to this thin boundary layer, and that is captured by this formula over here. So this CO star is essentially HO divided by pi A, where HO is the Henry's law constant for oxygen, which was a very large number. I can't remember now, which was given to you in the lectures. Now, of course, uh, we have now talked about the rate at which oxygen is being pumped in, partly by the liquid stream and partly by the transfer of oxygen from the gas phase to the liquid phase. But we still have to talk about the rate at which oxygen is being consumed and in the liquid phase. And the most obvious way in which oxygen is being consumed is, of course, the rate at which the cells are consuming oxygen, which is RO. This is the specific oxygen uptake rate, which has units of millimoles per hour per gram dry weight. So this is specific. This is called the specific oxygen consumption rate. So this is described on the basis of total dry weight or a per cell basis. Do you understand? This is each cell's, the rate at which each cell wants to consume oxygen. But this, of course, has to be multiplied by the total concentration of cells, which is in grams dry weight per liter, and RO times X, which has units of millimoles per liter per hour. This quantity together, this product, which has units of millimoles per liter per hour, is known as the volumetric oxygen consumption rate. This was the quantity we considered, when we did the first example. And of course, this has to be, I think that takes care of the whole thing. Yeah, yeah, that's it. Nothing more. So now, let's see. No, no, no. This has to be multiplied by. Wait a second. This has to be multiplied by the VL, the total volume of the liquid, because all this is happening in the. This is per liter. All these things are given. This, when you say liter over here, that is referring to the volume of the liquid, because the cells live in the liquid and consume oxygen also in the liquid phase. So now, dividing the whole thing by VL, from the left to the right, assuming that VL is constant, this implies that ddt of CO equals, here you get F over VL, F divided by VL, multiplied by COF minus CO, and then you get another term plus KL, and notice this is AI divided by V. I mean, I have an AI here, and then I'm dividing it by VL, and then CO star minus CO, and of course the last term simply becomes minus RO times X. So this term is describing the oxygen that is entering with the liquid stream. This term is describing the oxygen that is being transferred from the bubbles into the liquid. And notice the fact that now you're getting an AI over L, which is the interfacial area per unit volume. But that is exactly what we called, this entire quantity is exactly what we called A, interfacial area per unit liquid volume. So you can now see why we define the interfacial area on the basis of the liquid volume. It's because of this differential equation. You divide the whole thing by VL. That's where it comes from. So basically, ultimately, you end up with the differential equation that says that the rate of change of the oxygen concentration is equal to this you can, I don't know what to call it. Maybe we can just continue to call it D. This is strictly the residence time of the liquid. So this is D multiplied by C plus KLA multiplied by CO star minus CO minus RO times X. That is the main differential equation that we have. So this is the mass balance that we get for the liquid phase. Okay. Now, it turns out where CO star, I should add, where CO star is essentially, as I pointed out, pi HO divided by pi O. This is HO divided by pi O. So where pi O is the concentration in the gas phase. Okay. Now, actually, it turns out that in reality, the amount of oxygen, this term, in reality, many times, in fact, most of the time, unless you are not stirring your reactor enough, then the first term, this term, is usually very small compared to second term. In other words, physically what you're saying is that the amount of oxygen that is brought in, solubilized in the liquid phase, is really quite small compared to the oxygen that is being pumped from the gas phase into the liquid phase. So this is usually very, very small, and therefore you often work with the equation dCO dt equals approximately equals KLA CO star minus CO minus RO times X. And all this equation says is that the accumulation of oxygen is dependent upon the rate at which the oxygen is pumped from the gas phase into the liquid phase, minus the rate at which oxygen is consumed by the cells that live in the liquid phase. That's all. So stuff is getting pumped into the liquid phase where it is being consumed by the cells. Now, the second thing I want to point out is that actually, because the solubility of oxygen in water is very small, this is what you have, this is what you call the oxygen accumulation. This is how much oxygen is accumulation term, right? This is the rate of increase of the oxygen concentration in the liquid. Now, because the solubility of oxygen is very, very small, this term is typically quite small compared to this term and this term. For example, this might be 100, this might be 99, and this term might be equal to 1. So you do not lose much accuracy by saying that this term is essentially equal to 0. Physically, what it is saying is that you can't accumulate much oxygen. I mean, really, stuff just comes in and just goes right away towards consumption by the cells. It doesn't accumulate a whole lot because the aqueous medium that we have simply does not have much capacity to hold oxygen. It takes whatever it gets and immediately transfers it to the receiver, which in this case is cells growing at, the cells consuming oxygen at the rate RO times X. So that is the essence of the liquid phase balance. So we will use almost entirely the balance. This is the most general balance, but we will often be using this simplified form of it. This is the most common liquid phase balance that we will use. I mean, um, actually, I should correct myself. This is not always true. Maybe I should just leave this. This is not always true. So maybe we'll leave it at that. We will simply deal with it whenever the time comes. Sometimes you make the approximation, sometimes you don't. Okay. So if that part is clear, any questions about it? Any questions?
So none from my side.
Uh-huh. Then I'll move on to the next uh, which is mass balance, which is mass balance for the gas phase. For the gas phase. So again, for the oxygen in the gas phase. So now we're talking about the same working volume, demarcated in red. But now we're talking about the oxygen that is coming into this gas phase and leaving this gas phase. So if we lump this entire gas phase together, and so let's say we have DDT, okay, and I will use the notation. We're doing a mass balance here, so let me call C. Let me use the notation CO, comma G, and I use G to distinguish CO, which I have used over here, This is the concentration of oxygen in the gas phase, whereas this is the concentration of oxygen. This is the concentration in the liquid phase, and this is the concentration COG, denotes the concentration of oxygen in the gas phase multiplied by Vg. Okay? And that is equal to Fg in, which is the gas flow rate. This is the gas flow rate coming in, and let the concentration of oxygen coming in be COG in. There's too many subscripts, but I'm no choice. I mean, that's why we'll simplify it in a minute. You also have gas going out, so you write that as Fg out multiplied by COG out. And then, of course, what is the last term? Well, the last term is that this quantity over here, which represents the transfer of oxygen from, there's oxygen moving from the gas phase to the liquid phase. This is the one that appears over here. So this is KLA, right? Multiplied by, and this is KL. We already had an expression for this. This was KL multiplied by AI multiplied by CO star minus CO. That's the expression we had. So this is therefore equal to, this means that this is essentially I think this is the only form. We will not need to simplify this further. I think we need it only in this form. The reason is the following. We'll be using this ultimately. So at steady state, this will basically tell you that at steady state, we will need the steady state form of this balance later on. Okay, so this will only be needed once when we talk about how to calculate KLA using certain methods. So with that as the background, let's try a couple of problems now. These are example 1. This is actually example 2. This is minimum KLA. This is basically asking you what is the minimum KLA that is required for, I guess, maintaining a certain dissolved oxygen concentration. So whenever the word dissolved oxygen is used, it means basically it's a synonym for oxygen in the liquid phase. So it's the concentration of oxygen in the liquid phase. This is the kind of notation that is used. So this is actually a continuation of the example we did earlier, where we found, this is the first lecture on this topic, what we found was that at D equals 0.2 per hour, the cells consumed, we showed that the volumetric rate of oxygen consumption was equal to approximately 80 millimoles per hour per liter. So this is the volumetric rate of oxygen consumption at D equal to 0.2. This was, we took this example from actually Willardson's book, and it was basically during fermentation, ethanol fermentation, and this was the rate of consumption of oxygen by the yeast, Saccharomyces cerevisiae. And the question that we are now asking is, so we want to ensure that the dissolved oxygen concentration, that the dissolved oxygen concentration, which we have denoted by CO, this is the concentration of oxygen in the liquid phase, never falls below what they call the critical, and this I need to explain, the critical DO, dissolved oxygen concentration, which they call, the notation is CO critical, right? And basically that critical concentration is around 0.1 or 0.05 CO star. So basically when the concentration of oxygen becomes approximately 10% of the solubility, keep in mind this is the solubility of oxygen, CO star is the amount of oxygen that you will find in the liquid phase when, for example, the gas phase is in contact with it, right? So this is kind of like solubility of oxygen. And when the dissolved oxygen concentration becomes approximately 10% of this, so for example, if the solubility is 8 milligrams per liter, for many, many organisms, once the concentration falls to 0.8 milligrams per liter, or around 0.8, 0.5, something around that neighborhood, then they really start to experience a shortage of oxygen. So stated differently, if I draw this graph here, if you take a look at the specific growth rate of cells and plot the dissolved oxygen concentration, or what we call CO over here, you basically have a picture that is like this. And this critical concentration is something in this neighborhood. I should just make one of them. This concentration is called CO critical. If you go below CO critical, then oxygen actually starts to affect their value of mu. They actually start to experience oxygen limitation. And you really don't want cells to get into that zone. You want them to have plenty of oxygen. So you typically want to operate well above CO critical. And this CO critical, it turns out, is about, if this is CO star, CO critical is approximately 0.1 times CO star. I use the word approximately because it can be, 0.05, 0.02. It varies upon the organism. Each organism has its own critical oxygen concentration. But that's the general neighborhood. Is that part clear? Any questions about what I have said so far?
Yes, that's clear.
So now, the question is, what is the minimum value? What is the minimum value of KLA, right? That must be maintained. So physically, what we have here is we have this parameter KLA, which, as I told you earlier, can be changed by changing the power per unit volume. For example, by increasing the stirring speed, or by increasing the size of the impeller. Anything that pumps more power into the reactor will give you a higher value of KLA. So the question that is being asked is, if you go back to this equation over here, they have basically told you what is ROX that they have given to you as 80 millimoles per liter per hour. And they have also told you that this concentration CO must never go below zero point 0.1 CO star. That's the bare minimum you want. And the question that is being asked is, what is the minimum value of KLA that you should maintain in order to ensure that CO always remains above zero point 0.1 CO star? Is that question clear now?
Yes, sir, it is.
Uh-huh. So any thoughts on how we would proceed?
So I guess first of all, since the dissolved oxygen concentration should remain constant, like the LHS would like tend to zero. And since we're given K, we need to find we basically need to find KLA, and we are given like R naught into X, and the minimum value of C0 would be equal to 0.1 C naught star. So we can use that to so we can get 0.9 C naught star minus R naught X equal to into KLA equal to 0.
Into KLA into zero?
So, no, so no, not exactly that. So KLA
Uh,
into 0.9 C naught star minus R naught X equal to 0.
uh, okay, anyway. Maybe I think you're saying the same thing that I have in mind, but maybe the one way to look at it is KLA multiplied by CO star minus CO is equal to RO times X at steady state, right? These are the only two terms.
Yes, sir. Exactly.
This is Q naught, which is given to us. So this is fixed. This is given to us. This is the number that has been given to us as 80 millimoles per hour per liter. That number is fixed. Now, basically, what he's talking about is that if so, you can call the right hand side the demand side. This is the demand for oxygen, and the left hand side as the supply side. This is the rate at which oxygen is being supplied. The demand side is fixed in this question, and he's basically saying that what is the minimum value of C0, CO, if you want to maintain it above zero point 0.1 CO star, what is the minimum value of KLA you need? So to understand this, you can see, roughly speaking, that if the demand side is fixed, then the higher the value of KLA, right? If I increase KLA, so keep in mind CO star is also fixed, right? Because if you're blowing air through the reactor, then that air contains a certain mole fraction of oxygen. In other words, the partial pressure of oxygen in that air is a fixed quantity. And if that pi A, that partial pressure of oxygen in the bubble is fixed, then that means CO star is fixed. CO star, if you remember, is nothing but HO divided by pi A, where pi A is the partial pressure of oxygen in the bubble. And if that is like, for instance, air, you know that is equal to 0.21 atmosphere. So CO star is also fixed. You have only two things here to play around with, KLA and CO. And what is clear is that if you increase KLA, then it is clear that you can live with a higher value of CO. So essentially, what this is saying is, once again, if this is the boundary between the gas phase and the liquid phase, this is pi A, this is fixed, right? And let's say this is the value of CO star that is in equilibrium with it. And then this comes down like that and comes down to some CO. Now, let's say if you increase the value of KLA, right, then clearly So keep in mind that this demand is being satisfied by KLA multiplied by CO star minus CO. If I increase KLA, right, then I can live with a smaller decline because it's the product of KLA. So it's proportional to the gradient, but the proportionality constant, which I can change by changing the stirring speed. The higher the stirring speed, the lower the gradient that is required, the concentration gradient that is required to meet the demand. So as I increase KLA, it is clear that the concentration gradient will become milder and milder and milder. By concentration, I shouldn't say gradient, I should say concentration difference. So that's all there is to it. I mean, if that picture is clear to you, so it is clear intuitively that as KLA increases, yeah, it's clear that CO star minus CO decreases, right? Which means basically, since CO star is fixed, it means that CO is increasing. So you can live with a higher and higher concentration. And that's all there is to it. So, and that you can solve. You can see going back to this equation, call this equation star. You can see from equation star that KLA, right? I mean, this equation star immediately implies that KLA, I mean, maybe I should, which way should I, I think it's better to put it like this, which means that CO star minus CA equals Q naught, which is a fixed quantity, divided by KLA. And that implies that CO equals CO star minus Q naught over KLA. That's the expression you have. Well, this graph you can plot and you can see exactly what's going to happen. And this is the graph that you will get. Here I have KLA, here I have CO. And you can see that when you plot this graph, basically when KLA equals QO divided by CO star, so at this point, this is the point where KLA is equal to Q naught divided by CO star. It is equal to 0, and otherwise it kind of increases like this. As KLA goes to infinity, it approaches CO star. And that makes sense. The higher the value of KLA you have, the smaller the concentration difference that you can tolerate, which means as KLA goes to infinity, there'll be hardly any concentration gradient because KLA is so large that you need a very small concentration difference to satisfy the demand for oxygen. And this is the lower level. And what they're basically asking you in this question is, I want not 0, but I want it at 0.1 CO star. So basically, I need to keep my KLA above this value. I mean, so basically, are you with me? Just put CO equal to, I'm trying to show this thing graphically because the calculation is kind of trivial. But do you understand the physics now?
Yes, sir.
Is it clear to the rest of you? Bhavya, is it clear?
Yes, sir, it is.
Yes, sir.
Yes, sir.
Mm-hmm. So essentially, you have to basically make sure you put CO, you put it this equal to 0.1 CO star, solve for the value of KLA, and you will get it. But this is really what you're doing. You're trying to find out that value of KLA beyond which your oxygen, dissolved oxygen concentration will remain above zero point 0.1 CO star. Okay, where this graph is nothing but CO star minus Q naught divided by KLA. I'm making use of this equation here. Okay, so now that's actually one form in which this equation is used. Here is the other version. It's actually a variant of the same problem. So it is a variant of this problem in the following way. In this problem, the demand was fixed, right? I mean, demand is always equal to supply, but demand was fixed, and we were allowing something on the supply side to change. Okay. In the next problem, there is the demand itself is variable, and how? Let's just take a look at that example. This is actually example. I mean, this is 10.3, but this is taken straight from Doran. This is actually the most important, uh, if you will, um, thing to understand. So maximum cell concentration supported by oxygen transfer. So I think I mentioned this in the first lecture. I think I mentioned that actually all the nutrients are highly soluble and lots of it can be carried by uh, the liquid medium that is coming into the reactor. But because oxygen is not soluble, ultimately, how much biomass you can produce in a reactor is actually determined basically by how much oxygen you can pump in. That is what controls the concentration of biomass. And now we are ready to do that calculation. And we'll do that calculation by actually taking a numerical example. So it says that a certain strain of bacterium is cultured in a 15 cubic meter reactor. So the volume of your reactor, VL, is essentially equal to 15 cubic meters. The name of the strain is some Azotobacter vinylandi or something like that. I mean, who cares? It just move on. Uh, they say they are also telling you that this reactor is being operated at a KLA value and of 0.17 per second. So let me now emphasize that the units of KLA are 1 over hour. And to see that, recall that KL for us, according to the film theory, was nothing but DL divided by LL, where DL was the diffusion coefficient through oxygen, through the liquid, divided by LL, which is the thickness of the film on the liquid side. So this has units of centimeter per second, diffusion coefficient, and LL has units of centimeters. So that means KL alone has units of centimeters per second. So KL, let me emphasize, has units of centimeters per second. It has units of velocity. But what we are looking at is not KL, but KLA, right? This is KL multiplied by the interfacial area per unit volume. And A being interfacial area, I should just write the formula. This has units of interfacial area per unit liquid volume. So this has units of centimeter square per centimeter cube, which is 1 over centimeter. So the moment you multiply KL by A, you end up getting essentially 1 over time as your unit. And that's why it will turn out that this constant 1 over KLA is an important estimate of the speed of the transfer. Do you understand? I mean, if I write KLA is equal to 0.2 per second, it means that 1 over KLA, which is about 5 seconds, is the approximate time scale on which oxygen concentrations change significantly. This will come through later on when we go about it. But anyway, keep in mind that the units of KLA are per unit time. Okay. Now, the third thing that is given to us is that the specific, now in this case, notice that on the demand side, they are not giving us the volumetric oxygen uptake rate. They are simply telling you what is the specific oxygen uptake rate, which is, oh, sorry, one more term I need to mention. They have also given us the solubility of oxygen. So the solubility of oxygen is, they say, 8 into 10 to the power minus 3 kgs per meter cube, which sounds like a very fancy thing, but it is nothing but 8 milligrams per liter when you do the unit conversions. Okay, this is the standard number that is used. Okay, and finally, they are saying, so it's a reactor which has a volume of 15,000 liters. If you do it in, oh God, it's not writing. 15,000 liters, and the KLA is on the order of about the time scale on which the concentrations change is about 5 to 10 seconds, and the CO star is 8 milligrams per liter. And what they have given you is that the specific oxygen uptake rate is equal to 12.5 millimoles per hour per gram dry weight. So notice that they have given the uptake rate per gram dry weight, not the volumetric uptake rate. So really, if you take a look at your equation, which again says that at steady state you have to have KLA CO star minus CO equals RO multiplied by X. They have provided you this, but not X. In fact, the question says, what is the maximum cell concentration supported by the conditions in the reactor? So in this question, you are holding VL fixed, KLA is fixed. You're not allowed to change KLA. This is, of course, a constant because once you choose the gas phase, if it's air or whatever it is, you have fixed the partial pressure, and that fixes CO star. And this is also fixed. This is the oxygen demand per cell. So we have KLA is fixed, CO star is fixed, and RO is also fixed. And he's basically asking you what is the maximum value of the biomass, what is the maximum value of the biomass that you can sustain. And now, anybody want to take a shot on this? This is a slight variant where the demand side is not fixed. You can increase the demand by increasing the biomass. So what will happen as you increase? So KLA, CO star, and RO are fixed. And I'm increasing the biomass concentration. What do you think will happen?
So the CO value will keep on decreasing because the O2 will keep on getting consumed. So for the maximum value, like the dissolved oxygen should tend to zero. Because post that, you won't have any other growth.
So say that again. After that, you won't have any growth.
After that, you won't have any oxygen uptake basically by the cell.
So no oxygen uptake beyond that. So here the picture is, if this is the layer, and this is pi O, the concentration in the gas phase, then and this is the film on the liquid side, this is the film on the gas side, then CO star goes down like this, right? Now, what is happening here is that we are assuming that the concentration of cells in the liquid phase, you're allowed to change it. Now, as you increase X, clearly the demand side increases. To meet the demand side, the gradient. So since KLA is fixed, right? Since KLA is fixed, the only way to meet this enhanced demand is to increase the drop in the concentration. You know, basically, this is what's going to happen as X increases. So as X increases, the gradient goes down. So this is CO star. And of course, uh, this is X increasing. And this is the concentration. Of course, C, this is the picture that is emerging. This is CO in the bulk phase. Now, it can only go down until finally CO becomes equal to zero, right? I mean, you can't make this quantity any bigger than CO star. And once it becomes equal to CO star, because basically C naught has become equal to zero, you basically pushed it to the maximum limit. You're not going to get any more. So basically, essentially, the calculation here is to simply put CO equal to CO star, CO equal to zero, and that means, so this implies that X max, maximum value of X, is equal to KLA multiplied by CO star divided by RO. And if you have any difficulty understanding it, another way to write this is that under this condition, where X max is maximum, so this is also equally, the physical meaning is equally obvious here. On the left hand side, you are saying what is the volumetric rate of consumption. And on the right hand side, you are writing down the maximum volumetric rate of supply. So X max is reached when these two sides are equal. Is that part clear? So essentially, this is the formula, right? Where the numerator can be viewed as maximum O2 supply rate. Okay. This is in, this has units. The maximum, keep in mind, the numerator has units of millimoles per hour per liter of the liquid. The denominator, on the other hand, has units of millimoles per hour per gram dry weight. The ratio of the two gives you the maximum X. Is that part clear? Any questions on this part?
So it's clear.
So now I think we can. So this has given you a general feel for. I will just mention one or two things that are there in the book, but I'm not covering, and then proceed. So this particular derivation, this one, we derived the mass balance for oxygen in the liquid phase by assuming that the gas was well mixed. Right here is the assumption. Okay. And that's actually the assumption that certainly is the only assumption that you will see as long as you're doing academic work. But if you go to industrial reactors, then this assumption does not hold. The gas is not well mixed because the reactors are so large that sometimes you do not get good mixing. The real problem is kind of hard, but many people model that sort of situation by taking the exactly opposite and extreme view with regards to gas mixing. Instead of assuming that the gas is well mixed, thoroughly mixed, they assume that the gas undergoes plug flow, just as in the liquid phase. Well mixedness and plug flow represent two extremities, right? I mean, in one case, basically perfectly at the, all the way down to the molecular level you have mixing. Um, Plug flow means no mixing at all. The whole thing is moving literally like a solid slug. The same thing is true here. Instead of assuming that the gas is well mixed, people assume that the gas is kind of moving like a slug upwards through the reactor, right? So it's um, slug-like motion upwards through the reactor, and that leads to some changes in the final formulas. You end up getting this quantity called the log mean temperature difference, which you must have encountered in heat transfer also. But I'm just going to skip that. I mean, it's not relevant to anything that you might do at the academic level, and anyway, it can be understood easily. So what I'm going to get to now is really uh, measurement, measurement, measurement of KLA. And this is a question of how do you actually measure. So I have given you the theory behind it, right? We said that based on the film theory, KL is often described by the quantity dl divided by ll, and then a, we had a formula with a bubble diameter, and I mean, it was I'm trying to remember now, it was, I think, 6 over dB multiplied by gas holdup divided by 1 minus gas holdup, and then I gave you a formula for dB. So it's there's a formula for dV in terms of power per unit volume. This was given to you, but there are also formulas for epsilon, um, as a function of power per unit volume, and formulas, and it's sort of complicated. So really, in practice, uh, the the estimate. So in practice, um, one estimates one estimates KLA by a formula of the type, by a formula. This is empirical. I should say an empirical formula. This is an empirical formula, and it has the form KLA is proportional to, this is power per unit volume to the power alpha multiplied by u sub g to the power beta, where u sub g is what is called the superficial gas velocity. And this, you know what it means, right? Right? Do I have to define it? Uh, do you know what it means? Somebody can give a yes or a no. Yeah, please.
So
Huh?
we haven't heard of this quantity like in verbatim. Maybe we have heard of it in some different sense.
It is just Fg divided by the cross-sectional area, I should say, of the tank. So this is cross-sectional area of the tank. So actually, the real velocity of the bubbles is actually a little bit higher, because the bubbles do not occupy the entire cross-sectional area of the tank. They occupy only a certain fraction of the cross-sectional area, obviously, because the gas holdup is less than 1, right? So only some fraction of the total volume is occupied by the bubbles. So it should be no surprise that a similar fraction of the cross-sectional area would be occupied by the bubbles. So the bubbles are actually, the real bubble velocity will be higher than the superficial gas velocity. But this is just a sort of an empirical sort of number that works out quite well. Well, why does this appear? This appears because the gas holdup apparently is strongly dependent upon the superficial gas velocity. So it's coming from this epsilon kind of depends on U sub G and P over V. So the superficial gas velocity dependence comes from this P over V comes from the dependence of dB, which I had given to you. The bubble diameter depends upon uh, the bigger the power per unit volume, the smaller the bubble diameter. The smaller the diameter, the bigger the interfacial area, and therefore the bigger the value of KL. Sorry, the bigger the value of Ka. Similarly, the bigger the power per unit volume, the smaller the thickness of this film, this boundary layer. I mean, if you agitate the liquid very strongly, then the stagnant film becomes thinner and thinner and thinner. Its region of influence becomes smaller and smaller. So, but it's really hard to work with all these formulas. So people just work with this formula. This is the empirical formula that they work with. And as these things will give you these empirical formulas will give you accurate estimates up to 40% plus minus 40 to 50%. So what that means is you apply the formula to your system, you will get a value of KLA, but it can be either plus up to 50% away from the real value. So that is why in this area, experiments are key. Experiments are critical for measuring. For measuring. I mean, the theory can give you a guide as to what the important variables are, like you got, power per unit volume and superficial gas velocity. But the real measurement is becomes absolutely critical. So now the methods of measurement. Um, so let me start with the first method. The first, actually, I don't know if I should proceed. This is the easiest to understand. So this is the easiest method. This is called actually it's dynamic. I call it dynamic method. So there are two dynamic methods. This is the one that I call dynamic method without cells. And what do I mean by that? This experiment, I mean, this is not really true, and I'll get to it later on, but people believe that the rate at which oxygen is pumped from the gas phase to the liquid phase has nothing to do with the presence of cells in the medium. You know, so you can do the experiment without cells, and even if you put cells into the liquid medium, it should have no impact, right? Because the pumping process is a non-biological physical process. So we can just measure it without cells. And even if we grow cells in the liquid later on, nothing will change. This assumption is actually false for reasons you remind me, I can explain them to you later on. But here is how the method works. If this is the reactor, so first thing you do is you you deoxygenate deoxygenate the reactor. You deoxygenate the reactor by passing nitrogen through it. So through it. So let me first make clear what we are trying to do. What we are trying to do is we're trying to find out. We are running the reactor under certain conditions. So we have a certain impeller speed, we have a certain gas flow rate, you know, we have, composition of the gas is fixed. These are the conditions under which we will run the reactor. We want to know that when we are running the reactor under these conditions, what is the value of KLA, which is a measure of the speed with which oxygen is transferred from the gas phase to the liquid phase. That's the question. Okay. Now, the easiest way to find this is really just to do an experiment rather than sit there and work out with fancy formulas. And that experiment simply is this is your impeller, and this is your sparger, right? So, all the impeller speed, the gas flow rate, all the conditions under which we operate it, these are fixed at those values. But all we do is we change first. What we do is we pump nitrogen through this place. When we pump nitrogen through it, all the oxygen is removed from the reactor. So the reactor now is completely devoid of any, these bubbles are all nitrogen. These nitrogen bubbles, as they flow through, they keep on displacing the oxygen. And ultimately, you will have no oxygen in the liquid phase or in the gas phase. Okay? And then second, at time t equal to 0, at t equal to 0, you switch. You switch from nitrogen to whatever is the condition under which you will finally run the reactor. So if it is 99% of the time it is air that you run through the reactor, so you switch from nitrogen to air. As soon as you switch from nitrogen to air, now I should also mention over here that you're also making some measurements. So here, what you are measuring is the dissolved oxygen concentration, which I have called CO. This is done using a device called a DO probe, which you will see in your lab. So the picture we have is the following. If this is 0, uh, basically at time 0, you will have up to time, by the time you have reached 0, you have no DO, you're at 0. Actually, you have removed all the oxygen. At time t equal to 0, this is the point at which you are switching from nitrogen to air. As soon as you switch from nitrogen to air, you will start bubbling air through it. And when you do that, it should not come to you as any surprise that this concentration will start to increase. You will see more and more oxygen in the liquid phase, which is being picked up by the dissolved oxygen sensor. So it will increase like this, like this, like this, like this, like this, and then it'll finally reach a flat value. And what do you think that value will be? Anyone?
So CEO star.
That's right. So basically, the speed with which this rises, you can, it shouldn't be. I mean, the higher the value of KLA, the more rapid the rise. And how do you capture this? Well, you just come back to our differential equation, which said dCO dt equals KLA multiplied by CO star minus CO minus RO times X. But this experiment is being performed without cells. There are no cells here. So this is equal to 0. So all this is saying is that dCO dt equals KLA multiplied by CO star minus CO, where this quantity is again being HO divided by pi O, where this is fixed by the gas phase that you are using, you know, which could be air or which could be pure oxygen, depending on whatever you are using. And this quantity is also fixed, right? Because we have fixed the conditions, the RPM and everything else. And that's it. Solve this differential equation. This differential equation will basically give you an exponential change. Okay. I mean, uh, actually, you can easily see if you define a new variable, let's say, let's define a new variable z equal to CO minus CO star, which is, if you want to put it this way. Oh, okay, I should just, instead of going to solution, let me just mention what will be the initial condition here. This has to be solved with an initial condition, which is CO at time t equal to 0, which is the dissolved oxygen concentration at time t equal to 0. What is the initial condition?
So at time t equal to 0, CO is 0.
That's it. So if you solve it, it will give you something that says that basically CO is reaching CO star exponentially, right? It should not surprise you that basically what you will find is that initially it will rise. The slope has to become smaller and smaller because initially CO star minus CO will be very large. So CO is equal to 0. But as CO builds up, CO star minus CO will become smaller and smaller, right? Because the concentration difference is getting smaller and smaller, and ultimately the rate of change will be equal to 0. So this picture that I have drawn uh, with with this picture over here, decreasing slope, is obvious from this differential equation. As CO goes up, CO star minus CO goes down, and that means that dCO dt has to decrease. And that's exactly, solve it, you get an exponential equation. Rewrite that exponential equation in such a way that you can, plot log of this versus time, and you can extract KLA out of it. So that's it. That takes care of it. And we'll pick up on the remaining ones in the next lecture. Is that clear?
Yes, sir.
Okay.
Sir, sir, can you please send us the marks for the minor exam?
I will put them on Moodle.
Yes, sir. And sir, another question, sir. Are you free in any of the next few days?
No, it doesn't look like that, man. I just told you that I have, I think, 5 or 6 more lectures in the other course. So I'm really swamped now. I have no time. I'm giving one lecture every day.
Okay, sir.
So I mean, I'm afraid those who missed the test missed the test. You said that you would send me the cases of the real people versus the not so real people.
Yes, sir.
You have not sent me anything yet.
Okay, sir.
By the way,
I'll
but I have to. I will exercise my own judgment. I mean, there are some genuine cases
Yes.
whom I might ask some extra questions on the previous part.
Yes, sir.
But that will be almost certainly during the major itself. Not. I have no time between now and the end of the semester because these new lectures were given to me only last week.
Yes, you talked about that. Yes.
And they start, I think, tomorrow. Effective tomorrow, I have, I think, 5 or 6 lectures until the end of the semester. So I have no time. I will probably do it. And as far as the major also goes, I really don't know what the status is. I'm happy to do an exam in the conventional mode. By
Yes.
conventional mode, I mean you sit there and you give a written test. But that can only be if people have onboarded.
Yes, sir.
So is it possible if the students who have onboarded give the Viva instead of the written test?
I'm sorry, I didn't understand your question.
So since it was mandated that the students who have onboarded need to give a written test. So, but is it possible that the students who have onboarded give the Viva instead of the written test?
Actually, I'm not. It's too complicated for me to do it in 2 different ways. You understand? I will choose one way,
Yes.
and I will only go with the written test if everybody gives it. If people have not onboarded, it makes no sense because then it becomes subjective, right? Do you follow? I mean,
Right.
When I give a Viva, I'm judging everyone the same way. When I'm giving a written test to everyone, I'm judging everybody the same way. But if I give a written test and then to some and the Viva to some, it doesn't cut it. I'm not comfortable with it. So I think you had told me that everybody is going to get onboarded or something, Dave, right? But the more and more people are onboarding. What is the status now? What percentage of the students have joined the hostel?
Sir, not a lot of people will not everyone will onboard. That is for sure.
So it will not be 100% people.
No, sir, I don't.
No, sir, it won't be 100%. Like it might be close to like 60%, but it won't be 100%.
So I will just check with the head. I am personally not in favor of conducting separate exams. It makes it very hard for me.
Yes, sir. Yes.
I will just use one method. That's it. Okay. All right. But you have
Fine,
to
sir.
keep in mind that it will be a long. I mean, it took me more than 2 days to conduct the Viva.
Yes, sir.
And so, and maybe I think I've learned a few things from that. I mean, I think I spent too much time with some people. This time I will not give so much time. I think I gave virtually everyone 20 minutes. This time, if I find that people are, just not there, I might just end the damn thing in 5-10 minutes. Because I think I spent a little bit extra time. So let people know that, I spent a little bit of extra time with the people that were performing poorly, saying that they got zeros and that they need to sort of beef up and be a little bit more regular. But going in the final, I don't think there is any point in giving warnings. I mean, just over, right? There is no need to give any warnings. I'll just give 5-10 minutes and move on, because otherwise I have to spend like 3 days. So after all your majors are over, right? You have to keep, and at that time, if I hear this nonsense about I don't have time and my internet is not good and this and that, find a way. 15 minutes in 3 days is not that hard. So you let them know that these things will not fly at that time. Is that clear, Dev?
Yes.
Maybe
Yes.
you haven't seen these. I've seen these, right? I mean, there were people who for 2 days I have to go and help my cousin and I have to do this and I have to do that. None of these guys are going to get any opportunity now. It's the final, and if they blow off even the final, then it's tough luck. Okay.
Yes, sir.
Okay. All right. So see
Thank,
you on Thursday. And Monday. Okay.
yes, sir.
Yeah.
Thank you.
Thank you, sir.
Thank you, sir.